and welcome to the University of Michigan M-Flight Aero Design Team Flight Readiness Review. My name is Daniel Fuma, and I am the Chief Engineer and Flight Line Captain for the team. Now I'll introduce the rest of the developmental team as well as the competition team members. I'll start with Nidhi, our Flight Systems Lead and Ground Station Operator, and the other two Flight Systems Leads, June and Sam, as well as Vinny, our Structures Lead and Competition Team Safety Pilot. Brian, our Hardware Lead and Ground Station Operator, Selah, our Aerodynamics and Propulsion Lead, Ewing, our Manufacturing Lead and Competition Team Member, James, our Computer Vision Lead and Competition Team Member, Peter, our Graduate Student Advisor and Competition Team Member. And now I'll go into our Unmanned Aero System overview, called the MAP-4, also known as STAR. The MAP-4 is a fixed and high-wing design that employs the use of wingtip fences to reduce the induced drag on the aircraft, and it's powered by a single motor equipped with a 24x13 carbon fiber propeller. And the aircraft utilizes a ground station communication antenna and a telemetry antenna to stay connected with our ground station at all times. We also use a hardware and propulsion safety shunt plug so as to keep all members clear of the propeller arc while the aircraft is being powered for takeoff. We employ the use of a tail dragger so as to create space for our payload hatch underneath our aircraft. Now I'll hand it over to Brian for our hardware.
Here is a quick wiring overview of MAP-4. So to start off on the bottom, we have the software antenna on the right and the telemetry antenna on the left with the temporary camera in the middle for now. In the front part of the fuselage, we have the propulsion batteries, and towards the back, we have the hardware battery. And these could be armed in this, turned on and off with the shunt plugs located here and here. To begin, inside, we have the Pixhawk 6C autopilot system, which is connected directly to the Jetson Nano, which is our companion computer. And these two black antennas are used for the Bluetooth arming and disarming of the payloads. In addition, we also have the M8N GPS module, which sits on top of the fuselage's hatch. And we also have a servo driver that would drive some of the servos, including the revolver mechanism. This is the Ubiquity Bullet, which is a software transceiver, and on top of it is the RC receiver, and the information and the input it gets is sent to the PWM PPM converter, which translates the information that could be fed into the Pixhawk, which afterwards gets sent to the power management board, which takes in this information and sends it through the servo rails. And here we have the telemetry radio, which gets all the information like the telemetry and our airspeed and sends it back to our ground station. And on the back, we also have the extension antennas for the RC receivers.
As for computer imaging's hardware, we thought that using the Arducam 12.3 megapixel camera module and a CS mount lens with 25mm focal length was enough for our mission given our budget and the quality of images that we were trying to achieve from our cruise altitude.
On the software side, for detecting standard objects, we use canny edge detection to find the shapes from the images. We detect contours from the canny edge detection image and use the area and the number of sides of the contour to determine the type of the shape. After we determine the shape, we then crop out the shape from the image and find the most dominant colors in the cropped image. We assume that the most dominant color will be the shape color, while the second most dominant color is the character color. Finally, we use color masking to isolate the character from the image and pass it into an OCR for detection. As for emergent objects, our aircraft uses YOLO V7 to determine whether or not an object is humanoid or not. For our imaging and detection software, the accuracy for color is 90%, the accuracy for shape detection is 35%, and the accuracy for character detection is 75%. Unfortunately, we were not able to test and compare an object's real-time location versus the object's location calculated by the object detection software. Therefore, we are unable to provide information on how accurately our software can find the real-time position of a detected object. Therefore, we do not know the error for object location calculation. Therefore, we estimate that our detection accuracy is approximately 35%.
Talking about the payload housing itself, it's divided into two halves. The top half, which has the parachute and the avionics housing, and the bottom half that houses the payload itself. Now, the bottom half is easily removable so that we can get easy access to the payload upon recovery. And the parachute housing splits in two semi-cylindrical halves based on the altitude after it's dispensed. Each of the parachute housing is attached to the base of the avionics with a hinge and a spring loaded in order to stay open at all times. They are kept close together using the rubber band you can see, which is triggered using a servo. So the design of the aircraft was centered around the payload drop mechanism. This was to ensure that since the mechanism is housed inside the fuselage, there was a minimum drag, and since all the payloads are so close together, after each subsequent drop, there's a minimal change in center of gravity. The rotating rack itself is made out of 3D printed ABS plastic and some copper dowels. The payload is dispensed and loaded to the aircraft's belly, you can see in the animation on the bottom right. Now, the payload bay itself has a removable front bulkhead and servo-actuated hatch. This ensures that the payload is only dispensed when we actually want it to. Moreover, the drop mechanism itself is placed right under the quarter chord location, again, to prevent any changes in CG and make it easier for our flight system and flight software to deal with any changes after each subsequent drop.
Our airdrop mechanism's hardware mainly consisted of servos and an Arduino Nano 33BLE sense board. And so when the Arduino microcontroller receives signal from the Jetson Nano over Bluetooth to ARM, it allows the payload to be able to open up when it reaches a certain altitude threshold. And once it gets to the point, a small HS5055MG servo would then unlock a metal rod that would allow the parachute to open.
On a software perspective, to determine the location our aircraft needs to be to complete the airdrop, we first sweep the payload drop zone to acquire all images necessary for the computer vision software to locate all targets. Once all targets have been located, the computer vision software then sends the information to complete the following calculation to determine where the aircraft needs to be to drop each individual payload. As you can see, this formula takes into account the location of the target as well as an estimated drop time given the current altitude, the velocity of the aircraft, the wind speed at that moment, as well as the drag profile of the payload given the current air density. Once all calculations have been made, the flight system software then creates a set of waypoints for the aircraft to complete to drop all payloads. Concerning our airdrop's performance, unfortunately we were unable to perform a cumulative test of our airdrop system. However, through a unit test of our revolver mechanism within our fuselage, our parachute release mechanism, our parachute's ability to safely glide our payload to the target, as well as the structural stability of the tough PLA 3D printed material we were using, we believe it gives us a 30% accuracy with our airdrop.
As for our plane's communications, we're using two 900 MHz telemetry transceivers with a cylindrical long-range omnidirectional antenna that is attached to the bottom of the plane and a Yagi-Uda antenna on the ground. And as for our software, we're using two Ubiquiti Bullet software transceivers to transmit images and information about our software at 5.8 GHz. And with this, we also have another cylindrical omnidirectional antenna on the plane, and we're using a patch antenna on the ground. As for RC, we have an 8-channel main receiver with two additional auxiliary receivers sticking out through the back so that we have the max amount of reception. And our main receiver is also designed specifically for carbon fiber fuselages so that we have the best connection possible. And with this, we will be using a Spectrum DX8 transmitter on the ground with them connected at 2.4 GHz. Throughout our numerous test flights, we saw that we had a stable connection to all communication devices throughout all stages of the flight. As you can see on the right, even at the distance of 300 meters from the ground station, we still had a solid connection to our telemetry radio. In addition, we conducted an RC ground range test, which responded to our transmitter inputs even at a distance of 800 meters.
So to start off with an overview, our CG sits at 2.86 feet behind our nose, and our neutral point right behind it at 2.91 feet, giving us a static margin of 6.1%. The wingspan of our aircraft is 11.25 feet, and the height and length of our aircraft is 2.23 and 8.25 feet respectively. For our initial sizing, we sized around the design space with a maximum takeoff weight of 45 pounds, which includes our payload of 1 plastic water bottle. As you can see from our sizing plot, we are most constrained by our climb and stall curves, but with a thrust-to-weight ratio of 0.41 and a wing loading ratio of 3.09, our design point is within the feasible range. In terms of aircraft configuration, we went with a box and wing configuration with high semi-tapered wings and wingtip fences. We used the MH114 airfoil with a high aspect ratio, which is better for long endurance flights. Our tail is a conventional rectangular tail, and we use the NACA 0012 airfoil. When initially sizing for our wing geometry, the design goal was to minimize the weight while achieving the necessary lift, which is why we went with a semi-tapered design, which is better for efficiency and included wingtip fences to lower the lift-induced drag. When sizing for our tail, we did initial sizing using the volume tail coefficient method, and then further refined those dimensions through trade studies in AVL. And we use a tail boom of 3.17 feet, and the horizontal stabilizer and vertical stabilizer metrics are shown on the slide. For dynamic stability, we tested the dynamic stability of our aircraft against the Cooper-Harper scale, which rates stability on a scale of 1 to 9, with 1 being ideal. And the 2 configurations we tested for were the empty and fully loaded for 4 different modes of flight. And as you can see, we meet the requirements and our aircraft is dynamically stable. So next, moving on to propulsion, we have selected 2 Tatu 8000 milliamp hour batteries, which are connected in series. And these are 6-cell lipos and have a combined weight of 5.17 pounds. So we've tested the endurance of these batteries at 80% charge and full throttle, and we found that it sustained our system for 20 minutes, which is sufficient for flight. Next, our aircraft features our Hacker Q80 motor, which has a low KV of 225 RPM per volt, and it weighs 1.15 pounds. So we use this in combination with a carbon fiber 24 by 13 inch Falcon propeller, and we use a low KV motor along with a high diameter and high pitch propeller for efficiency. And we found that this combination gives us 16.2 pounds of static thrust.
Hi, I'm Vinamra, and let's talk about the structure of the aircraft. To begin with, MAD-4's fuselage is constructed out of carbon fiber, which allows us to maximize its internal volume while minimizing its weight.
Our fuselage is manufactured entirely out of carbon fiber composites due to its high strength-to-weight ratio and ability to be molded into complex geometries. For every part of the plane needed to be made out of composites, we route out high-density polyurethane molds and go over iterations of sanding and painting to give it a smooth finish. Using these molds, we prep wet layups and sandwich epoxy-wetted carbon fiber of 90 and 45-degree orientations, unidirectional carbon fiber, and an 1/8-inch foam core. It's vacuum sealed and left to cure for 16 hours, where it solidifies to become what we have on our plane. Our wings and tail are constructed out of composites, leading edges, and laser-cut wooden ribs. The majority of the ribs are from an 1/8-inch balsa wood. The parts that do bear weight are cut out of an 1/8-inch light plywood. All balsa-to-balsa interactions are joined with fast-curing CA glue, while all other wooden interactions use slow-curing CA glue. Any interactions of composites are bonded with Capisil. Control surfaces for the wing and tail are attached via nylon hinges, and we apply ultracoat over all uncomforted sections of a sealing iron to form their smooth and uniform skin.
Our aircraft performed very well during all flight tests, successfully landing and taking off and cruising through all of our flights. We were able to perform 7 total flight tests, one of which included a stall test where our safety pilot was able to successfully recover our aircraft after stall. We were also able to successfully tune all PID constants and pixel constants for our aircraft to perform autonomous waypoint navigation.
To achieve autonomous flight, we use an autopilot. For our flight controller, we use the Pixhawk 6C, which is running the Autopilot plane firmware. This supports manual control via an RC controller, but also supports autonomous mode via predefined waypoints. We also have a companion computer on the plane, which is the Jetson Nano, running Ubuntu 20.04. And this is able to read telemetry from the Pixhawk over Mavlink and send this back to our ground station on the ground. We also use Mission Planner on the ground station to visualize waypoints and other telemetry data from the Pixhawk. To avoid obstacles, we detect them with millimeter wave radar, which has a conical field of view. The detection range of 150 meters allows us to dodge potential collisions. We have a radar facing up and down. Obviously, this leaves a blind spot in front, but we aimed to maximize our potential to avoid collisions. Then in our flight system software, we simulate having an ADS-B receiver. Our new plane has built-in support for avoiding aircraft detected with an ADS-B receiver. Our alternative is to detect objects with the radar and then pass ADS-B Mavlink messages to the Pixhawk to simulate the Pixhawk detecting ADS-B objects.
In previous years, M-Fly Autonomous has been plagued with crashes that have prevented us from attending the SUAS competition. This year, we've mitigated the risk of crashing by adding redundancy into our system with the construction of a test plane and also implementing a competition-ready drone. Both of these options have given us critical redundancy to test and implement our software, as well as take the first step to making M-Fly a team at the SUAS competition. We've also taken a lot of safety methods in the implementation of shunt plugs, servo locks, a dual battery system in case of a power outage, an antenna, a parachute, and our payload, and multiple flight line practices, so all members of the team are all prepared for all situations.
We're past 1,000 feet.
Oh!
This second flight is indicating our second requirement, which is to fly 250 feet away from the safety pilot autonomously. We did this by initiating the RTL mode on our aircraft, as you can hear indicated in the video, when we switch from manual to RTL.
Alright, we're switching.
Unfortunately, due to inclement weather in the days approaching the FRR deadline, we were unable to film or fly our aircraft to complete the third requirement for the flight readiness review. However, with the 7 test flights we accomplished, as well as all PID constants tuned on the PICSOC, as well as testing done on the drone and our test plane, we are confident that given an additional day of good weather, we would be able to achieve the final requirement of flying the 12 miles fully loaded autonomously, as we had already flown autonomously, demonstrating our RTL capabilities in the previous section of this video. In conclusion, the MAP 4 is a fixed and high-wing design operated by the PICSOC 6E and the Jetson Nano, with a carrying capacity of 1 payload, 45 pounds fully loaded, and 20-minute flight time. We expect to score about 50% with the MAP 4, and we believe we are competition ready. Thank you.